Okay, good morning. So let us continue our exciting lesson of integers. So I hope that you enjoyed the calculation last time. By no means you don't need to learn it if you don't want to, but it was, I think, fun to see how it goes, and you see how much mathematics you indeed know right now. So we were able to follow all these steps in complete detail. I was just not talking general ideas. I was just talking all the details, and hopefully you were following. Yes. Now let us try to review a little bit what happened last time, the salient points. So here, let me just now be a little bit more generic. Yes. So I have the coordinate axis, and let me just draw any arbitrary function. For example, this graph is like this. And then, as usual, in this course, we always treat well-behaved polite functions. Means that they are continuous without sharp points, okay? And then, instead of starting from 0 to 1, in the previous example, if you remember, I talked about x squared function. And I started from 0 and I continued up to 1. But this is not a necessity. What is necessity for our discussion is that our function be a well-behaved function, meaning it is continuous and it is without sharp points. And if you go to a little bit advanced mathematics, you can also relax these two conditions. You can just ignore them and it still works, okay? But let us, for the time being, be more concrete. So let me just try, instead of going from 0 to 1, let us go from an arbitrary number. So let me call it A, and then I will go up to another point. Let's call it B. And you are interested in this area that you see here, yes? You want to find that area. But I want to use the same tricks as before. Okay, so what was the main points in that derivation, do you remember? So I was trying to approximate my area with the sum of the areas of rectangles. Yes? So I want to do the same thing here. So, and then the idea was to increase the number of partitions. Because if I just take one big rectangle, for example, here, of course, it is approximately equal to the area that I want, but the area that I am making is substantially large, okay? But if I want to make the error smaller and smaller, we'll learn that if I increase the number of rectangles involved, every time that I increase the number of rectangles, I am actually reducing the error. Yes? So it is good. And then we realize that it doesn't matter if I divide it to 1 billion rectangles, 1 trillion rectangles, the approximation becomes better and better, but it will not be the precise value. And intuitively, it becomes hopefully clear for us that if I partition it to infinitely many rectangles, and if I succeed to calculate the sum, that infinite sum, then it might be a good idea to call that number the area. Yes? Is that clear?
Yes.
Yeah? Okay. Now let us do the calculation a little bit here again, in a general context. I haven't given you the function, I haven't given you the number, that's just generic context, but what I'm actually demanding right now is the function is continuous. One more thing is that the function for the time being is always above the x-axis. We will talk about that, what will happen if some part goes below the x-axis, or if the whole graph is below the x-axis, okay? So for the time being, let us have it. So do you remember what I'm supposed to do? I need to start partitioning this interval to n equal pieces, and then at the end, I want to send n to infinity, yes? So if I want to partition this, if I ask you what is this length, so the length, let me write here, whatever we do. So if I ask you what is the length, you subtract the number on the right minus on the number on the left, it becomes this length, and you divide it to n equal pieces. And then this is common to call this value delta x. Okay, this is the x increment. This is the change that you make for x values every step that you put in, yes? Okay, so in that case, do you remember a was 0 in the previous example, and then b was 1. When I subtract them, and then divided by n. That is why 1 over n appeared all the time in those calculations. That is, I'm just giving it a name today, delta x, yes? Okay, and then I start partitioning my interval to n equal pieces. This one, for definiteness of discussion, I call it x number 0, okay? And the last one, I call it x number n, yes? But then the next one will be, I will call it x1. So if I ask you what is this length, you can answer me. The length is just delta x, yes? So I have divided it into n equal pieces. Each piece I call it delta x. Then I go to the next one. How much further? Delta x more, yes? Then I get x2. And I continue this, for example. Okay, if I ask you what is the first interval starts from x0 to x1. What is the second interval? It starts from x1, goes to x2. So if you continue in this manner, at some point you reach to the kth interval. So can you tell me what is the kth interval? So this is delta x. It is between which number and which number?
xk minus 1.
X sub k minus 1 up to xk. Why? Because when I said this is the first interval, this index on the right was 1. Yes?
Is delta x always the same amount?
Yes. Delta x is that number. Yes. I take this length and divide it by n for all of them. And then when I say x, the second interval, you see the second index ends with 2. Yes. So first interval from 0 to 1, the second interval from 1 to 2, the third interval from 2 to 3. So the kth interval will be from x sub k minus 1 to x sub k. Understandable? Yes. Okay. And then of course I can also continue later. Yes. And I reach to that. But let me just concentrate here. So do you remember I started constructing a rectangle here? Okay, and then let me make it solid line here. Okay, so here I constructed the rectangle. Do you remember something like this? Okay, so and then I want to find the area of this rectangle. Of course, I want to do this for every rectangle that I have. But this is just one representative. I don't want to distract you by drawing all of them. Yes? Okay, now if I ask you, what is the area of the kth rectangle? So that is the kth interval or the kth rectangle, yes? Kth rectangle. And if you don't mind, let me call the area of the kth rectangle a sub k. Okay, can you just write a phrase for me here? And so what do you think? Exactly, this rectangle is equal, the area is exactly equal to what? The width, which is delta x, yes, multiplied by the height. But what is f? What is the height?
F of k.
F of x sub k, yes? Because this is x sub k, and this becomes the height. So this becomes f of x sub k. Is that understandable or not? This is something that you have to know very good at this level. Whenever you want to find the height on a graph for a given number, you put this number into the function, you get that. Yes?
Okay, so do you know how long the length should be when you want to draw that rectangle, or is it even important?
Yes, you need to find the maximum one so that whenever you make a rectangle, one part of it lies outside.
Would you say that's precise, or?
No, that's not precise.
Okay.
This is precise. This is the area of this hatched rectangle. But the area that I am interested in is just this below this. Yes?
And could that height of the
This is the error.
could that height of the rectangle go above the local maximum point of our graph?
Not in this case. No. I'm always concentrating on the highest point to make the rectangle.
Mm-hmm.
So even if I reach here, then the highest value is that one. So whenever I want to construct a rectangle, if the graph is going down, and if I concentrate here and here, then I will not make this rectangle, I make the bigger rectangle. You can decide. either always to find these rectangles that lies a little bit outside, or you can work with minimum. So people can also call this, they can construct the inner rectangle. And then I will tell you, if you do this with the bigger rectangles, the sum that you get is called an upper sum. It's not mentioned in the book, but these are the terminologies. If I use these rectangles, the sum will be called a lower sum.
Okay.
I will come to that later. But this, what I have written here, is exact as far as I am concerned about the area of this rectangle, which of course is not exactly the area that I want to calculate, because this part of this rectangle is outside the area that I want to. Okay? But the lesson that we learned last time is that when I increase the number of rectangles, I will also demonstrate it using GeoGebra for you today, and then you see that when I increase the number of rectangles, the errors that I am making are shrinking actually. So that's the whole point. So this is the area of this kth rectangle. But how many rectangles are involved in rectangles? Yes? The first rectangle, the second rectangle, the kth rectangle, and the nth rectangle at the end. Yes? So if I ask you, can you give me an approximate value for the area that I am interested? So if you don't mind, let me call that area A without any subscripts. That area is approximately, not exactly, equal to the sum of all these areas. Sigma means sum, but K goes from the first rectangle up to at most nth rectangle. Yes, understandable or not? Okay, and then what I do, and I take this one and put this instead. Yes, so this becomes now approximately equal to this, but from here to there is exactly equal. Sigma K goes from 1 to n, f of x sub k delta x. Yes? So now this area is approximately equal to this, but this one is exactly equal to that. So this means that this area is approximately equal to the last expression. Yes? And now, if I want to make this exact according to what we learned, what I need to do, I have to start increasing the number of rectangles infinitely to infinitely many. So this means that what we learn is that the area that I am looking for is this sum. You can write in principle K goes from 1 to infinity, but this is not the proper way of writing. People write K goes from 1 to n of the same expression, and then take the limit and n goes to infinity, yes? What we learned is that this formula is a reasonable formula for the area that I'm looking for. Yes?
Why do you say that A is almost equal to sigma AK, when AK and f of xk times delta x is the same thing as AK?
No, AK is the area of this blue region.
Yeah.
But this area is the one below the curve.
What I'm asking is, if a sub k is equal to f of xk times delta x,
Yes?
and when you put that in to the area, it becomes exact, not almost.
Yeah, this is still, I'm saying this is exact. But this is not exactly equal to this.
So A is not exactly equals to the second expression.
No, because this one is equal to the second expression.
Okay.
And so A is approximately equal to this, but this one is exactly equal to that.
Okay.
So this means this is approximately equal to that.
Okay.
Okay, so this, what I want you to understand, that this formula is reasonable formula for finding that area that I am interested in. But you might feel that this is not possible to work with the formula because you have to have infinitely many rectangles. But the calculation that I did, even though it was very messy and lengthy, but we were able actually to find the area using this formula. So it is possible, but probably not very efficient. And I told you that not only it is not efficient, sometimes it becomes impossible. Even for very simple functions like a square root of x. And do you remember what was the obstacle? When we want to calculate that, we need to sum up some numbers, some series. We have to calculate a series. And if you remember, most of the calculation I did was related to calculate that sum. But sometimes that sum is impossible to calculate in a closed formula. So this means that even though this seems damn right, but it doesn't work. Okay? So we have to find another way. But for the time being, let us keep this limit in front of you. Okay, and then what is important is actually, so what you are doing in geometrical sense, you are approximating your function with step functions, yes? So what you are doing, you are saying that, okay, this is a curved part, but instead of having this curve, I replace this curve with a straight line, yes? And if you go to the next one, for example here, I don't know, for example, you have it here, the next one. So what you are doing, again, you have a curve here, you just pretend that curve is not there, you replace it with a straight line. Okay? So this means that it seems that you are breaking, so don't look at this curve, just concentrate on these bits. So what you are doing, you are actually breaking the curve and then making it to a small horizontal part so that you can work with. So what you are doing, you are just throwing this part away and approximate this part by a horizontal line, hoping that you are not making that much error. And of course, if you are making it smaller and smaller, really this error becomes smaller and smaller. So what is important? You are taking a curve out and replace it by horizontal line segments. Of course you are making an error, but this error becomes smaller and smaller. This idea is extremely important. So what you are doing, you are replacing a curve with step functions, like steps, yes. That's what you are doing. Is that understandable? Yeah. So assume that, I don't know, if you have a lot of stairs here, you want to go to the second floor. I don't know, someone strong can shoot you up and then you follow a curve there, or you can go stepwise up. So this is the meaning of integral. So that curve is the real trajectory you take, but this stepwise is just you are breaking the trajectory into pieces and then you're going up. That's the whole point. Yes? Okay, forget about this problem. Now let us go to physics problem. Again, what we want to do, if I ask you, this is an extremely simple question. If I ask you, you have a particle, just for simplicity, moving in one direction, always to the right, for example. If I tell you that the speed, so I can talk about speed rather than velocity, because I'm asking that the particle is just moving in one direction, okay? So, V, I give you it's 5 meters per second, okay? And then I ask you, so the particle starts when the time is 2, and then ends when the time is, say, 10. And I am telling you that this particle is moving with constant speed, 5 meters per second. So how much this particle will travel when it reaches to 10 seconds during this time interval? It's a very simple question, yes?
50 meters?
40, yes.
40.
Yeah. Because you say that the time interval is how much? 8 seconds. And each second it moves 5 meters because that speed is constant, be careful. Then you multiply these two numbers, you get 40 meters. That's a straightforward question, yes? Is that clear? It's very simple, yes?
One question there. If we have a function that it comes from the third part of our coordination system.
No, I told you that this is not allowed yet. I am just thinking about a function on top.
Okay.
Yes. I will come back to that. So, this is a straightforward to answer, but now assume that this particle is not that nice particle. It starts moving with different speeds at different times. Yes, so it means that the time is no longer, the speed is no longer a constant speed, but it varies according to time. Yes, which is more reasonable. When you start the car, it's very hard to drive with a constant velocity all the time. Okay, so it means that now how do you answer the question? Because you start the timer 2 seconds and then you stop it when it is 10 seconds, but you have a particle which does not move with a constant velocity. The velocity of the particle depends on time. So at each instant of time, the particle is moving with a different speed. I hope that at least you agree with me, this problem is not simple as before. So just I want to understand, but this problem has an answer, because you have a car, is moving with a different speed, the car is moving, it doesn't even know that you are measuring something, but you are also measuring with the timer. And then when the timer is finished, you can see how much the car has moved, independent of at some points he moves faster, at some points slower. Is the question clear? The same question, but with a particle with varying speed. Yes.
Isn't that just acceleration and deceleration?
No. That is acceleration, deceleration in physics, but I don't care about that one. I'm not talking about acceleration. I am talking at, if I wait 8 seconds for this particle moves 40 meters. But another particle is moving with a velocity which depends on time, and I want to see at the end of this time interval how much the particle has moved. That's a sensible question again. I want to ask about this particle, yes?
Is it the area of, if you draw the graph of the...
Yeah, but
function?
that is coming, that they are trying to sell this to you in physics.
Yes.
But it comes in mathematics. Why is that right? Why do you think you should calculate the area below some curve, and that is the distance? We want to understand that.
Because you have delta x and t,
Yes?
and not every material is that one.
No. That's not exactly that. I want you to see exactly, I have to do a process exactly identical to this for solving that problem. I just want to motivate. So assume that you want to solve this, okay? So how do you solve that? You would say that, okay, this particle is actually, so what I do, so let me just do this. Instead of this one, instead of having the x-axis, I would say that this is reasonable to call it the time axis, okay? And then instead of saying t is equal to 2, so if you don't mind, to be general, let me write t a seconds, and then I end somewhere at t b seconds. And the particle is moving with a speed, but at different times it has different speeds. We want to do this. So what do? Again, you have to do some approximations. It's inevitable. So what you do, first you divide your, for example, time interval to 2 equal pieces. Okay? And then you assume that your particle is moving. Of course, your particle speed is also changing even during this time interval. But you can pretend that your value is a constant value, v of a. You can approximate all these velocities with the value of the velocity at this point. Of course it is wrong, because this particle might have different velocities in the middle. But you can approximate it with a constant va. Yes? And then, for example, if this reaches to this point, from now on you can approximate all the velocity with vc. Okay, and then you can calculate, because you say that how much I have been waiting here, c minus a seconds, and then I have this speed times that, it becomes the distance. Yes? And I will do the same thing here, so vc multiplied by b minus c. And this is the distance approximately traveled by my particle during this interval, and this is the distance traveled by my particle during this interval. If I add them, I get an approximate value for the distance of my particle during the whole interval. Is that understandable? But it is clear it is wrong. It is not precise, not completely wrong, but not precise, yes? Because I told you that. There is no reason that I believe the speed of my particle is constant here, because I told you that the speed of the particle is changing every time, yes, in principle. But let me do this process. And I want to do the same thing here. Yes, so let me just clean this. And clean this. And now let us understand that I want to divide my time interval to n equal pieces. So how much would be the length of each time interval? The whole time interval is b minus a. I divide it into n equal pieces. And I call it delta, what do you think I will call it? Delta t, yes, because this is the t-axis. So I call it delta t, yes? So then let us concentrate again. So you will start, then I give this the name t initial, t naught. And then I will give this the final time t. And then I will start what? Subdividing this. So this is the t1, this is t2. If I ask you what is this length, you would say it's delta t. If I ask you what is this length, you would say delta t. And then you continue as before. You see what's happening? So I continue this. And then I reach to the kth interval. I hope that you agree with me. This is tk minus 1, exactly as before, yes? And now what I do, I approximate the value. I would say that, okay, can I say the velocity of the particle is constant here? No. But the velocity of the particle, I can call it velocity at t sub k minus 1. And I multiply it by delta t. If I ask you what is this is the distance traveled by my particle under this assumption that the speed of my particle is always the same as the speed of my particle at this time, which is not completely true. Yes? But it's a good approximation if this interval is short, because we live in this world. If you don't give time to a moving particle, the particle will not have enough time to change the speed dramatically. Yes? Even if that's a photon of light, yes? So, I mean, if I give a very short chance, a very short time for my particle, the particle, even though can still change its speed, but not that much, because the time interval is short. And if you don't like it, make it even shorter. Who cares? Yes. Even if you don't like it, make it even shorter. But making time interval shorter and shorter means increasing the n value to bigger values. Yes. Because n is the number of subdivisions. That's exactly the same problem. I just want you to feel that this is a physics problem. That's a geometry problem. But the method that I'm trying to solve both is exactly this identical. Yes? So if I ask you what is this, you will tell me this is the distance traveled by my particle approximately on this time interval. And if I am interested in the whole distance traveled, what you do? You just add them up, yes? Now if I ask you what is this, you would tell me this is the approximate total distance traveled by my particle during this time interval. But how can I make it more precise, better and better? By increasing n. And if I want to have the real precise value, I have to do the same thing. I have to divide it to infinitely many parts. So what I do again, I would say that, okay, the distance this time is equal to the limit of this expression when n goes to infinity. Yes. And now if you compare this problem with that problem, they are really understandable that they are the same, except for the numbers and letters. Yeah? So, of course, k has been replaced with k minus 1. And I told you that here, I chose to work with the bigger one, but I could have chosen to work with the smaller one, so it doesn't matter that much. So, but I want you to see that the structure of this limit and the structure of that limit are exactly the same, even though that is a problem on a different context, in a different context, geometry, finding area. That is a problem in physics, finding the distance traveled by a moving particle. But if I want to solve both problems, I have to calculate that kind of limit. So do you remember the motivation that I gave you for the derivative? I gave you exactly two perspectives. Once, Leibniz problem. Leibniz was interested to find an equation for the tangent line, which was a geometry problem. But Newton was interested to find the instantaneous velocity of a moving particle, which was a physics problem. But the way that they used to solve these two problems were identical, and it gave rise to a particular kind of limit. And then we called that limit the derivative because it not only appears in these two contexts, but in a lot of kind of applications. And that's also true among not infinitely, but millions of applications of these kinds of limits. So I just wanted to motivate you. This kind of limit in mathematics is also important. And whenever this happens in mathematics, if you are a mathematician, you say that, this is a nice limit, and this appears a lot of places, let me understand this once for all. And then they start giving it a name, and then understand its properties. That's the way that mathematics works, yes? And then they have chosen to call it an integral, okay? So this one, if I want to write this, they write this as integral of the function involved. And then instead of writing dx, they write, instead of delta x, they write dx. I will talk a little bit about that. And then they put the numbers here and there. Okay? And this is actually a good symbol, because if you look at the back of this tree, this is just S. And S sits for a sum. Yes, but it's not that beautiful probably. I don't know, is it more beautiful if they stretch this S? Okay, so the integral is actually a stretched S, but that's a good name. Why? Because whenever you are dealing with an integral, you are just adding numbers. So you are doing a sum. Yes? So you are calculating a sum when it comes to an integral. So remember this. This is extremely important because many people know how to calculate integrals, but they don't know what integral means. What an integral means in the first place. That is bad. Of course, you can be very skillful in calculating integrals, but then you don't understand what the integral is in the first place. So whenever, this is important, whenever in some kind of application, in physics, chemistry, biology, whatever, you are facing yourself with such a limit, you need to think about integrals. And so you can solve that using integrals, yes?
Yeah, we might maybe discuss this later, but there's like some few, like there's one with like a circle in the middle.
No, that is completely different. Forget about those things. That would be the university. Okay.
And there's also one that's like a straight line after with the derivative.
No, we'll talk about that.
Okay.
Yeah. Okay, so what I want you to understand, so if I want to write this in this symbol, how do I write this one now? I would say that integral, the function involved is v, but this is not a function of x, it's a function of time. And then instead of delta t, you write dt. And then, of course, I have chosen the same numbers, a and b, so you write from a to b. That would be the distance traveled by this. But of course, this is nothing for the time being. That is just a symbol that I have introduced. But this sum is what we call an integral of a function. Okay? Is that clear? Okay. So let me write a formal definition here. But it is extremely important. Let me just emphasize again. What is the meaning of integral? Understanding the meaning of an integral is important. And that is not complicated. Whenever you are dealing with calculating a sum like this, that a function is involved and an increment in your variable involved, but you want to send n to infinity, then you are facing what we call an integral. Then it is another question, how we can calculate integrals. We learned that the very inefficient way of calculating integrals is calculating the sum involved and this limit. But another one that we will talk, that is Newton's method. Okay? That it was very, very short. But for the time being, I want to write a definition of an integral formally. Okay, so formally, let me write definition. Okay, so now after mathematicians realize that this is important, they just start giving it a name. They're very formal. So let f be a function for the time being at this level that is continuous, on the interval x between a and b. Yes? Okay. The integral. So this is the word that I wanted to find. The integral of f on this interval is denoted by this symbol, a stretched s from a to b, f of x dx, and is defined as follows. Okay? So integral from a to b, this is the way that you read it. Integral from a to b of f of x dx is the limit of a sigma f of x sub k delta x, k goes from 1 to n goes to infinity, where xk is an arbitrary number in the kth interval. After partitioning the interval into two equal pieces, into n equal pieces. And by the way, at the level of matrix, you don't need to be that worried about the formal definition, but whatever you just learned is enough. You don't need to be very, very precise in your defining things. Okay, so there are some terminologies going on. These people call it the upper limit. I want you to know these names. The upper limit. Of course, the name of this one becomes very clear now. The lower limit. And then this function that sits inside the integral sign, where should I write? It's called integrand. Yes? And this, what you see, is called the differential of x. This is a little bit different from differentiation, okay? They are related, but the differential if you ask me how can I imagine delta dx, I would say that, how do you imagine delta x? Do you remember? Dx is the infinitesimal version of delta x. Yes? So dx, if you want to write something, dx is the infinitesimal version of delta x. Yeah? And it has another role for you, I will talk about that, but this delta x, you can imagine the very, very small delta x, we call it dx. So these names I want you to know. Lower limit, the upper limit, the integrand, the differential of x. Okay, so there's one question left that I haven't addressed yet, but you have some clue about it. How we can effectively calculate integrals, we haven't addressed it. Okay? But I can say something. So, but you know that this is written there. So from now on, if you want to find that area, there are some exercises in the book. They have drawn a graph for you, and they have colored a region, and they have just asked you to write the area in the form of an integral. They haven't asked you to calculate the integral, so you need to know. Yes? That's it. Okay. If you don't mind, I would say that this would be a good point if we can go to GeoGebra and try to understand things a little bit better. If I remember, of course, the syntaxes that I have to use in GeoGebra, we will try to discover, okay? Please let us record everything, because otherwise people think that we are crazy. Yes. We can repeat this part. Oh, I forgot to record. And you can say, oh. Okay, now it's more natural. And then people, when they look at the video, they realize that there is some mistake going on. Okay. Okay, but anyway, I will stop here, and I think even at this level, you can solve one set of problems. And the good thing about this book is that this is really talking about how to understand the Newton's method, not just by writing the formula and use it, but somehow how to prove it. Okay? So we will talk about that later, but there is a set of problems that you can work on it today, and I will write it here for you on Google Classroom. Okay, no questions? Thank you very much.